Welcome to the fourth lecture of week 2, which is on continuous filtration as well as industrial equipment for filtration. So, this series consists two lectures, lecture 4 and lecture 5. In lecture 4, we will discuss continuous filtration and different equipments involved in filtration at industrial level, and description of these equipment will be discussed in fifth lecture of week 2. So, let us start with fourth lecture of week 2, which is on continuous filtration. Now, what is continuous filtration? In lecture 1, 2 and 3 we have discussed the batch filtration. In batch filtration different steps were involved, and in each case once we remove the cake which is formed on the filter media, after that only we can start second cycle. So, continuous filtration is what? Continuous filtration we can define as continuous removal of the cake, because we won't allow cake to deposit for longer time, and therefore once the cake formation is enhanced or is increased, the filtration process stops. So, in continuous filtration we do some arrangement so that the cake which is formed on the filter media that continuously removes. So, in continuous filtration we go for continuous removal of the deposited cake. The cake thickness is thus not allowed to increase to large values, and therefore the filtration process can be conducted at constant rate employing a constant pressure difference. Now, if you remember the batch process, there we have defined two phenomena. First is the constant rate and second is the constant pressure. Now, pressure, why we increase the pressure? Because after some time when the filtration is carried out, after some time the cake deposition cake is formed over the filter media, and which offers resistance in the path of liquid to move, and therefore we have to increase the pressure. So, if you remember the batch process, there we have defined two phenomena. First is constant rate and second is constant pressure. Now, once we operate the system, after some time cake is formed over the filter media. For example, this is the filter media, cake formation appears over here, and as the thickness of this cake increases, this cake is basically this cake offers the resistance in the path of filtrate to move, to cross this, and therefore after some time the filtrate which has to pass this, its volume is reduced after continuous operation, and as this thickness of the cake increases, the volume which is collected as filtrate that is decreased. So, that rate of filtration cannot be maintained. So, to maintain that rate of filtration we have to increase the pressure so that it can be operated at constant rate. However, in continuous operation, in continuous filtration what happens? The cake is continuously removed. So, cake thickness cannot be increased, and therefore the rate of filtration is not affected by the formation of cake, and therefore at constant pressure we can maintain constant rate phenomena. Now, when we go for the batch filtration, what are the different steps? If you remember, the steps were filling with the slurry, then cake formation, dewatering, washing, again dewatering, and then cake removal. All these steps, apart from this there was another step which was about cleaning, dumping and reassembling of the system. As cake is removed continuously, there is no need for reassembling, dumping, etc. So, all these steps which were involved in batch that can also be involved in continuous filtration. And here we have rotary drum filter, which is very common example of continuous filtration and which is operated at vacuum. And in this diagram you see, here we have the rotary drum filter which has a specific diameter as well as length, and it is operated at vacuum. Now how it is operated, that can be illustrated through this animation. If you see, this drum is continuously moved or continuously rotates. Some section of this drum is submerged into the slurry, and if you see this some curved bar is there. So this curved bar is basically used for uniform mixing or homogeneous solution of slurry, homogeneous slurry. Now as some section of this rotary drum is submerged into the slurry, and all these, if you see in between lines, these lines are connected with the vacuum pump. So this system is operated at the vacuum. So once this system is submerged into this, it sucks the water, and during this sucking of the water, sucking of the filtrate, the cake formation occurs over here. So when we go for the different step, filling is basically submerging of this drum into this slurry, then cake formation, it means it sucks the filtrate, and due to this cake formation occur. Then once it revolves, once it leaves this slurry, it comes in this section. If you see, here we have complete formation of the cake, and here whatever water is available, that is again taken by the these lines which are connected with the vacuum. So here we have the dewatering step. Once the dewatering process is completed, we should go for the washing. So here you see cake washing is done. Here we have the assembly to wash the cake, and when the cake water is washed over here, again that water is sucked by these tubes, and after washing again here we have the process of dewatering, because whatever water is available in this cake, that should be taken by these tubes. And after that here we have the knife which is continuously taking this, continuously removing this cake. So once it will be again submerged into the slurry, the cake formation starts. So it will be used as, it enters as almost fresh drum. So you see, all these steps are involved in batch process also and in rotary process also. So if all these cycles are covered in one rotation, whatever steps involved in batch, all these are involved in rotary drum or continuous filtration in single rotation. So when we compare continuous filtration as well as batch filtration, one rotation of continuous filtration is equal to one cycle of batch. So in that way we can correlate batch filtration as well as continuous filtration. Thus the equation developed for batch filtration can be used for continuous filtration as well, keeping in mind that equation stands for one full rotation of the drum. So when whatever equation we have derived for batch, that we can also use for the continuous filtration process, but whatever filtrate we will obtain by this, that will be the filtrate collected in single rotation for continuous filtration. That all we have to see. So the final filtration equation, if you remember, this we have derived in lecture 2 of week 2. So time value from this, when we integrate this, we can get the time expression in terms of volume, where T is the time of cake formation, and if you see here we have the volume V collected, and once we collect volume to be collected, that is the time of cake formation also, because here V is the volume of filtrate. So in whatever time filtrate is collected, in the same time cake formation is carried out. So T is the time for cake formation, and if Tc is the time for one full rotation of the drum, then we can relate T with FTc. Tc, you remember, Tc is the time for cake formation, and that happens in one full rotation when we apply this particular equation. So if Tc is the time for one full rotation of the drum, then we can correlate T, that is the time of cake formation, is equal to F into Tc. Now here what is F? F is basically the fraction of cycle available for cake formation, and that is fractional submergence of the drum in the slurry. So F, how we can define the F is the section of the drum or surface of the drum submerged in the slurry, that we can define as F. So usually it is considered as 20% of total surface is dipped into the slurry, is submerged into the slurry. So in that case F should be 0.2, and V is the volume of filtrate collected during one rotation of the drum, and V by Tc stands for rate of filtration. So for compressible sludge, using Sperry correlation, we can have FTc equal to mu F alpha naught V by 2A square minus pressure drop power 1 minus S into V square, and similarly another factor for media, filter media, that is Rm mu F by A delta P into V. So this equation we can use for constant pressure and compressible cake in continuous filtration. So as the concept of constant rate and constant pressure is not applicable in this case, this particular equation is used to calculate time or time required for full rotation for compressible cake. So if you see this particular slide, here rotary drum vacuum filter is shown, which we have just described. Now if you see this figure, here we have the knife which continuously removes the sludge or removes the cake which is formed over the drum, which is shown over here, and after removing this, the drum re-enters into the slurry tank. And here in this figure we describe the operational flow sheet, because this is the continuous process. So what happens, rotary drum is associated with this slurry tank. So through slurry tank, feed enters into this portion is merged into this, and here we have the level control. Level control is to ensure that some certain section of the drum should be submerged in the liquid. When liquid level enhances, then this it is recycled back to the slurry. When liquid level enhances, then the liquid is recycled back to the slurry tank. So slurry is drum is submerged up to here in the slurry tank. The whole washing process is carried out. Whatever scrap is there, that is whatever cake is there, through knife it is collected into the solid collection tank. And then the filtrate, how the filtrate is collected? Through the tube which we have just discussed. Those tubes are connected to the filtrate receiver, and whole system is connected to the vacuum source, and then filtrate is taken out through pump for different use. So here we have the complete flow sheet for continuous filtration. Now to demonstrate how the calculation of continuous filtration is carried out, we have taken one example. And here rotary drum filter having diameter 1.2 meter and 1.2 meter length as well. It handles 5 kg per second of slurry containing 10% of solid when it is rotated at 0.005 Hertz. By increasing the speed to 0.008 Hertz, it is found that it can then handle 6.2 kg per second slurry. What we have to calculate is percent change in amount of wash water which may be applied to each kg of cake caused by increased speed of rotation of the drum, and what is the theoretical maximum quantity of slurry which can be handled. So you see, what we have to find is the amount of wash water. So we have to first calculate the rate of washing and then amount of wash water we calculate for case 1 where rotation is 0.005 and for case 2 where rotation is 0.008, and then we compare these two amount to calculate the percent change. So here we have the solution for this problem. This is the final filtration equation for single rotation. After rearranging we can obtain this expression. Further rearrangement gives this particular expression, and so we can calculate dV by dt by rearranging this expression, which is looking like this. And then after solving this, we can, what we have done over here, if you see, a square delta p divided by alpha mu f v we have taken out. So in bracket v plus a mu f Rm by alpha v. So you consider, if we consider this particular expression, all parameters available in this is a constant which we have denoted as a. V is there and all these parameter club into one and it gives a constant b. So we can write whole expression, that is dV by dt is equal to a by v plus b, and further integrating it, it gives v square by 2 plus bv plus at. Now here for case 1, one revolution takes 0.005 hertz, which is equal to 200 seconds, and rate should be equal to V1 by 200. How the rate is defined? Total volume collected divided by total time required. And similarly for case 2, one revolution takes 125 seconds and rate should be V2 by 125. Now from these two expressions we can relate V1 and V2, which is shown over here, and V1 by V2 we can define as 1.329 and further V2 should be equal to 0.75 V1. Now in the previous slide we have derived the expression of volume and time, and that expression was V square by 2 plus BV plus AT. Now for case 1, V1 square plus 2B1 plus 2A into 200, and similarly for case 2 it should be V2 square plus 2B V2 equal to 2A into 125. Now putting the value of V2 from this expression to here and then calculating the expression of A and B, we can get A as 0.00375 V1 square and B should be equal to 0.25 V1. Now the rate of flow of wash water will be equal to final rate of filtration. This we can consider. So for case 1, wash water rate should be equal to A by V1 plus B. That you can see from the last slide, the rate of filtration how we have defined, and similarly putting V1 we can calculate, we can find the wash water rate for case 1. So wash water rate per revolution is proportional to 200 into rate of washing, that is A by V1 plus B. So wash water required per revolution. Similarly, wash water per revolution per unit solid is proportional to 200 A by V1 plus B. Now here you can see we have defined per unit solid, but we are considering volume over here because volume will be associated with the solid which is forming the cake. Therefore we can use this per unit volume instead of per unit kg of solid. So this is proportional to 200 into, we can put the value of A which we have seen in the last slide, and we can put the value of B also. After solving this particular expression, we can say that wash water per revolution per unit solid is proportional to 0.6, and similarly for case 2, the wash water per revolution per unit solids is proportional to 125 A by V2 plus B. and after putting value of A and B over here, we can find this is proportional to 0.625. So percent increase is 0.625 minus 0.6 divided by 0.6, so that is 4.17% increment we have observed while increasing the revolution of rotary drum. So here we have to calculate theoretical maximum quantity of slurry which can be handled. For this we should know the rate of filtration. If you remember, this expression we have already derived in a previous slide, and then rate of filtration for this, from this equation we can calculate V by T as A divided by 0.5 V plus B. Now this rate of filtration is affected by this volume, otherwise A and B are the constant. So highest rate can be achieved when we are considering V as 0, and that value comes as A by B, which is equal to 0.00375 V1 square divided by 0.25 V1, and it gives 0.015 V1. On the other hand, for case 1, the rate should be V1 by 200, and this we have derived, this we have seen in the last slide. Its value comes as 0.005 V1. So when we compare these two, this is the present rate of filtration and this is the highest rate of filtration. So when we compare these two, we can say the highest rate of filtration is 3 times more than the present rate of filtration, and therefore as for a slurry it can be handled at maximum, at optimum condition, or maximum slurry it can be handled is 3 times more than that is used for case 1. So therefore for case 1 it was 5, so now it should be 15. Hence the maximum quantity or limiting rate is 3 times the original rate, and therefore the maximum slurry that can be handled is 15 kg per second. So that's all about the continuous process. Now we will discuss what are the different equipments available in industry for filtration. So first of all we will speak about classification of cake filters. First we have batch pressure filters. Here we have plate and frame filter press and pressure leaf filters. Batch vacuum filter consists vacuum leaf filter, and further continuous pressure filter, if we speak, we will see rotary drum pressure filters in this category, and in continuous vacuum filters we see rotary drum filters as well as disc filter. Along with this we have centrifugal filters which can be operated for batch as well as continuous operation, and under this category filtering centrifuges are found. So these are some of the classification of different cake filters. Now here we have seen one condition, that is under vacuum, and second is at normal condition. So what is the advantage and disadvantages of vacuum filtration? Advantages are, it is continuous operation because continuous removal of cake can be observed over here, which is not possible for non-vacuum processes. Second advantage is producing relatively clean filtrate, convenient access to the cake for sampling, like we have continuous removal of cake. So if we have to take the sample for the cake, that we can take very easily. Easy control of operating parameters such as cake thickness, because we do not allow cake to form over the filter media for longer duration, therefore it is continuously removed, so the operation becomes easier in this case. Wide variety of materials of construction. Along with this there are some disadvantages also. The higher residual moisture in the cake, because after one cycle cake is continuously removed, so dewatering is not carried out up to sufficient time, therefore cake which we have obtained through this is moist in comparison to cake which we have obtained through normal or pressure condition or batch process. Difficult to clean, mainly as required for food grade applications, and further high power consumption by vacuum pump. So, if you see vacuum in during vacuum operation, vacuum pump is operated continuously, which consumes significant power. Therefore, as far as operational economy is concerned, this is more expensive in comparison to batch. So, these are advantages and disadvantages of vacuum filtration. So, here I am stopping this lecture. We will discuss the equipment of filtration which are used in industry in next lecture of this series. So, that is all for now. Thank you.